Yeah, just try to be on that side of the camera for us.
Well, it's 4 o'clock, Jim.
Yes.
Yes.
It's not quarter till.
Quarter to 8.
So that clock is correct twice a day, right?
Yes, I like mine. Why don't you stand over there?
Okay.
Let me introduce you. It's my great pleasure to actually introduce Compton James Tucker III, eminent graduate of Colorado State University. He got 3 degrees here, starting his first degree in biological sciences in '69 and getting his Ph.D. in 1975. And one of the things that Jim did while he was here is, as part of his thesis, he developed this technique of looking at, monitoring green vegetation, the normalized difference vegetation index. And that has really allowed ecologists to really look at the Earth in so many different ways, and he'll describe it. And so from that effort of looking at grassland ecology all the way up to looking at trees, he's done a lot of great things. So after his PhD, he got a very prestigious post-doctoral fellowship at NASA Goddard, which he's been there ever since.
Yes, I was rehabilitated by NASA, and I'll explain why after my talk.
But Dr. Tucker still maintains a very strong link to CSU all these years. For over a decade, he worked with Dave Randall and his group and Scott Denning up in atmospheric sciences as part of a NASA team that led linking remote sensing to modeling and political sciences. Michelle Betzel was with you all, and education outreach. And so he really maintained a very strong presence with the interdisciplinary team here at CSU. He continues to write papers with Bill Parton on grasslands and connecting remote sensing to our modeling efforts on grasslands. So in many ways, Compton has paved the way for researchers, practitioners, and decision makers to really see the seasonal cycle, the Earth, the planet in various ways, from the early technologies in the 70s here in our rangelands, all the way to looking at high spatial analysis of regions of the world. He also pioneered the use of Landsat data with David Skoll to look at deforestation in the Amazon, really looking at
habitat fragmentation.
And habitat damages and restoration conservation efforts in the Amazon. So he keeps on using that and combining this land cover work today with advanced resolution sensors, with machine learning. He really has used his innovation to continue these developments. But he doesn't just do that. He doesn't do this nerdy remote sensing stuff. He also was part of a NASA team, NASA Space Archaeology program that led to using ground penetrating radar technology and magnetometry to look at ancient sites in Turkey, around Troy, around the Great River Valley, and at Gordian, the home of King Midas. So he's gone on to actually use remote sensing to identify biological hotspots. And then recently, showing his age, he's actually been promoting the discovery of fossils around Goddard Laboratory in Maryland.
Cretaceous fossils, not contemporary fossils.
He has co-authored over 190 journal articles, been cited. He's probably the most cited CSU graduate in history.
Oh, that's awesome.
I bet you'd be way up there. He's a fellow, AGU fellow in biogeosciences, AAAS fellow as well. He's been recognized internationally for his exceptional scientific achievements at NASA. He's gotten the Core Award from the USGS, the Galathea Medal from the Royal Danish Geography Society, the Vega Medal from the Swedish Society of Anthropology and Geography, and I can go on and on. He's also, like me, a winner or awardee of the Mongolian Presidential Award or something like that. So he and I actually established or reestablished the remote sensing capabilities within the Mongolian Institute, or Ministry of the Environment, where he donated the equipment, I delivered it, and became honored members of the folks there in Mongolia. So we go way back.
Well, Dennis, thank you for a very
Brief.
thorough. Okay, so before I start, so number one, you know that I'm a WASP by my name, right? Compton James Tucker III. Secondly, when I said I was rehabilitated by NASA, when I was, after I finished my master's, I was arrested in Fort Collins by the campus police off campus for misdemeanor marijuana possession. And they were going to charge me with a felony, but my dentist in Fort Collins intervened, and they only charged me with a misdemeanor, and also my roommate Brent Holman the same way. But I had to sign an agreement saying if I violated the terms and conditions of my suspended sentence, I would plead guilty to a felony and go to Canyon City for 2 years. So that put the fear of God into me, and I thought, I don't want to try my luck with her. And so I finished my Ph.D. in about 16 months. And then I got a postdoctoral fellowship at NASA, and they rehabilitated me because they hired me as a civil servant after I'd been there for 1.5 years. So, but all of my degrees and all the things I did have come from my work at CSU. And what I'm showing today will in part be attributable to that. It's a pleasure to be here. And then recently, so there's life in the old dog yet. We published a paper last month in Nature on the 2nd of March, and here's the title. Here are all the authors. In addition to leading the work, I had to keep order within the authors because any sort of disagreement could have sunk the paper, but it didn't. Anyway, so that's the paper where we mapped tree crowns over an area as large as the United States and Alaska combined, the continental 48 states and Alaska, and converted them into carbon at the tree level, at the 50 centimeter level, using 50 centimeter satellite data. So this is just a summary. We used 1/3 commercial satellite images over 10 million square kilometers, 90,000 training data, the learning part of our machine learning. We burned a lot of high performance computing on an NSF machine called Blue Waters. We had to operate upon an array of 2 times 10 to the 13th elements. And we mapped 10 billion tree crowns greater than 3 square meters area in the 0 to 1,000 millimeter per year precipitation zone. And we converted those into carbon via allometry, and there was a total of 0.8 petagrams of carbon in leaf, wood, and roots, and I'll show how this happened, at the tree level. Then we put ourselves into a box, because how the hell can anyone use something like this? 10 billion things. So we wrote a viewer, which enables people to go in and look at every aspect of our output data and find areas where we made terrible mistakes, where we had cloud cover, where we had aerosols, and where things went right. And at the tree level, see what the carbon was. So this is the second paper in the series. We had a proof of concept paper, also in Nature, where I was the second author. The first author, Martin Brandt, was the person who selected 90,000 trees of training data, which was a heroic activity. We only used 11,000 Maxar images there. And then we have this follow-on paper, which was just published, where we used 1/3 images. And we actually mapped 13 billion tree crowns, but we converted to carbon only 10 billion of them. I'll explain why. So this is what the landscape looks like. You're south of the Sahara Desert in the semi-arid zone. This is from the Sahelian zone, a place where I've worked since 1981, off and on. And you have scattered trees. This is what the landscape looks like. It's for the most part pretty flat. There's a marked rainy season on top where everything is green, and a marked dry season in the bottom. This is a photograph of gray tapins. And so we use data in the early dry season when tree crowns are still green, but nothing else is. So the herbaceous vegetation is senescent. Here's an NDVI profile with the range of data in the bottom from this portion of Senegal, 1/4 degree by 1/4 degree. And this is what the landscape in that area looks like. One of my graduate students produced this plot. We define a tree as something with a green NDVI crown in this false color image with an associated shadow. And this is how trees differ from the background using planet data on the left-hand side. This is just a shot showing the NDVI image. The pixel to each square is 50 centimeters by 50 centimeters. NDVI on the left, and this is the panchromatic band, so you can see the shadow. It's maybe easier to look here. This is looking in a three-dimensional plot at this tree. It's the same tree, pan data, panchromatic data, NDVI. And you see the tree crown, and the shadow has to be in conjunction with it, or else we call it not a tree. Here's an example. Here's one tree, and there's all of this vegetation, herbaceous vegetation, tussocks of grass. There's the tree right there, and we don't map all of these areas. If they have a shadow and they're not green, they're not a tree. If they're green and don't have a shadow, they're not a tree. Okay, so we mapped a total of 13.1 billion trees in this area, going from 9.5 north to 24 north. Now, we also mapped 1.6 billion bushes of crown areas between 1 square meter and 2.75 square meters. We don't include those in our study. And for this paper, we dealt with 9.9 billion trees from the 0 to 1,000 millimeter per year precipitation zone. So this is clearly a semi-arid application of what we did. It gets to be kind of mind-boggling, and I apologize if this becomes boring. So here's just an idea of what things look like on the ground. Here's what the data look like in the middle, and here's what our neural net detects as trees using our machine learning approach. Now, when you do a study like this, the first thing you have to do is determine what is the uncertainty and what are the sources of the uncertainty. So the first thing we did, we wanted to know how well our neural net worked. So this means if we were to do it again, we would have postdocs or graduate students do it, but we decided to do it ourselves the first time. One person did this from our team because we want to work out the method. And so they selected almost 6,000 tree crowns. Those are the green blobs you see there. And they were defined by the red circle or line around each of the tree crowns. And then we mapped them with our neural net using machine learning and our training data. And the difference was 2.5%. So we take this as being an indication that our mapping uncertainty is on the order of plus or minus 3%. And that's just the mapping of the tree crowns. Now, we also undertook, and I took part in this as well, the omission and commission errors. So that means if you omit a tree, that's an omission error. And if you call something a tree and it's not, that's a commission error. So we did this for about 1,256 by 128 meter areas. And what we found was that most of our errors were for the smallest canopy sizes, but they were fairly balanced in terms of omission, commission. And if we look at this plot over here, you see the same thing here. We have a huge number of areas where we had very few errors, and then we have a lot of errors down here. So overall, we had a net uncertainty. We had 5% for commission, 3% for omission, and a net of about 2%. So we take these as being our uncertainty, only for the tree crown mapping. Now, this is one of the areas I studied. I took part in this, and this also became my Christmas, Hanukkah, and winter solstice card in 2021, just because of the colors. So when you work with satellite data, you have opportunities like this, and you can't let them pass by. So the editors at Nature really liked this. And I don't know if that helped us get the paper published, but they said it was the most unusual Christmas card they had received. So this is just a mapping where I analyze it. So if it's a tree, it has to have a green canopy and it has to have an associated shadow in the direction of the away from the incoming solar flux. So you see all that here. This is not a tree. This is not a tree. But this over here is a tree, and it was an omission error. So the score here was 67 trees mapped correctly, 1 tree mapped incorrectly or omitted. in this case. Now, this was one of the good areas. Here's one of the bad areas. This is an area where there's a lot of bushes. And bush mixed trees and bushes can be a giant pain in the neck. And this was no exception. So if you look down here at these three trees, you see the associated shadow away in the direction of the away from the incoming solar flux. Here, here, here. And then you look at some of these trees and you see they have shadows all around them, all around here, the same here, so on and so forth. So this is an example of bushes being categorized as trees in the areas where I've circled in yellow, and areas where things are circled in white, they were mapped correctly. So bushes were a big problem. We have tried to solve that in our next run. And then I thought we should look at some areas of, now these were all randomly selected. So I drew one of the burn scar areas. And little did I know this would be a really accurate area, because the burn killed all the bushes and removed all the herbaceous vegetation. And so there were only 4 or 3 errors here. One was this weird thing here, and then there were 2 omitted trees. So a total of 3 errors. And that's because the burn helped simplify the ecosystem. We thought it would be the opposite. So that was one surprising thing. Now, with mapped tree crowns, how do we go from tree crowns to carbon? We use allometry. And so these are the data we use to go from crown area to leaf carbon. In this case, dry mass, and we multiply that times 0.47 to convert into carbon. Here's the crown area. We didn't have many root samples. The next slide will show you why. And we went to dry mass of roots, again, multiplied times 0.47 for carbon. And here is wood over there. So we had a total of about 700 samples of allometry here, 26 here, and over 900 here for leaves. Now, there's no other alternative to go to biomass because we don't measure height. Now, we may have height in a few areas for a few places, but not for 10 billion trees. Okay, so here is the allometry team in the field led by Pierre Arnaud, someone I've worked with for almost 40 years. And here they're working. So here's a tree which they're digging out. Now, I'm glad as a graduate student, postdoc, I never had to do work like this because it's hot, it's far from anywhere. There's not much shade, and if there is, you cut it down to sample it. And so you can see they've actually dug down like this. And here I think they've extracted the taproot. So this is why there are so few samples of roots. And you can see things as they progress. Our data were collected largely in this area. If you look very carefully, you can see that. A detailed paper on our allometry was recently published in Forest Ecology and Management. And we have all kinds of pictures like this and boring information there. And all of our allometry, well, it's not boring, it's very important. And all of our allometry is also with our data at the Oak Ridge National DAC for every tree in terms of the wood and the root and the leaf conversion of crown area to carbon. Okay, so our overall uncertainty, our mapping uncertainty was plus or minus 3%, a little over, maybe say between 3 and 4%. Our error of allometry was about 19.5%, and the total error is plus or minus 20%. So the uncertainty which we have is about plus or minus 20%. And that's also the uncertainty from the JEDI NASA Laser Altimeter mission for their carbon estimates by 2 very different methods, but not for the same area because they can't work in semi-arid areas. Okay, in our Nature paper, these are some of the summaries. On the left-hand side, we show the megagrams of carbon per hectare versus rainfall for wood, root, and leaf. And you see the leaf portion is very small. And the right-hand image, you have the megagrams of carbon per tree. You multiply megagrams times 1,000 and you get kilograms. These show the distributions. And all of these are in our Nature paper. And this is what it looks like, entitled Root and Branch. And if anyone can tell me what that means, yes, Dave.
Any idea why the carbon has a max of like 800 and something and then goes down?
No, we're puzzled by that. It could be land use changes, more agriculture and fewer trees, but we haven't investigated that yet, and we're very puzzled by it. So that's on our list of things to see what's going on and why. Okay, now these are interesting. On the left, we have the probability distribution function for carbon, and it just shows you, and then at the top, it shows you the amount of carbon in each of our three areas, the hyper-arid, arid, semi-arid, and subhumid, and also what the corresponding precipitation levels are for those zones. And then on the right-hand side is a cumulative distribution of the trees per canopy size. And what you see is that 50% of our trees have a crown area of less than 15 square meters. And so that's about 50%. We were very surprised by that. We didn't realize there were that many small trees. This is true for the subhumid areas and the semi-arid, the more humid areas, as well as the other areas too. Now, 90% of our carbon was in the semi-arid and subhumid areas, even though that only occupied 30% of our study. And that can be gleaned by looking at the top of the figure on the left. So the first thing we did was to compare our data to other published papers. The other published papers are in the box below, and then our paper comes along here, and then plus or minus 1 standard deviation. And so we don't agree very well with any previous studies. We're somewhat similar to what Niall Hannon did in purple, but otherwise there's a wide divergence. And so we think the problem is that in the semi-arid area, they were incapable of mapping individual trees. Now they might say, no, but this was our interpretation. And then on the right-hand side is just a summary. We were on the low side. This is for above ground carbon, but we have about 0.7 petagrams of carbon, plus or minus 20%. And then here are their figures. I think we have a very accurate uncertainty analysis or approximation, much better than using data where you cannot resolve individual trees. Okay, so now we take the other studies. This is above ground carbon, and we have these figures, and you'll notice that in 4 of these, that you'll see these concentrations of data above the line. They're the ones on the left where you have curves above ours. But here we're comparing 30 meter or 250 meter or 1 kilometer data to 50 centimeter level data. So it's an interesting comparison, and you end up with these clouds of points. We can certainly improve what we're doing, but I think you can't measure carbon in semi-arid areas unless you can resolve individual trees. Now we compare our data on the left again. You've seen this figure from the previous 2 slides, and we compare it to model results from the TRENDY models. And so here are our data, and this area in sort of this bluish color, that's the plus or minus 1 standard deviation of the TRENDY models. And the reason these models don't do too well is because they don't have accurate data for the density of individual trees at the 50 centimeter level. And that's represented here. These are the forest fractions used in each of the TRENDY models, as you see below. And so better data like ours will lead to better model results. That's the conclusion of this. Here's the summary figure in our paper, where we just have this figure comparing 4 other studies to ours in terms of the spatial distributions. I won't dwell upon that. So this is what happens when we start and we map tree crowns. We convert them into carbon in trees. We then convert that into carbon per hectare. And then here's the combination. And all of these data can be accessed at the Oak Ridge National DAC in our data repository. In some areas, you see you have 2 time periods. Here in this area in Senegal, you have more than a 50% accumulation of carbon in trees with a much longer residence time than herbaceous vegetation from 2002 to 2021. So there's undoubtedly, there's a huge carbon sequestration potential using these techniques. And this could only be improved in the future, but it gives an idea what could happen when you plant trees and then protect them. And major droughts don't come along. So we started off with 90,000 square kilometers, or 90 million square kilometers of data, and then we down selected to just under 10 million square kilometers of data for our study area. We got all the data gratis from the National Geospatial Intelligence Agency because they had already been purchased by the US government. And some far-sighted person there put in the contract that these data could be distributed to government agencies for their use in whatever they were doing. The USGS, NSF, it doesn't matter. As long as it's a US government agency, you can access and use these data. The problem is getting a large mass of them and having it organized so you can do something with it. So then we down selected to 9.7 million square kilometers. Most of our data are from the early dry season, November, December, January, and that's what we use in our paper. This just shows you where we had the data and what satellite they came to or came from. Then I got really, when you do a paper like this, you get concerned about errors. You lose sleep at night. You worry about things that haven't happened yet. And we all know that's a bad sign. And alcohol wasn't a solution. So we decided to investigate aerosols and cloud cover. So this is an aerosol effect of a dust storm in our study area, photograph taken from the International Space Station. You see all this dust. You see the front of the dust storm coming along the bottom. And then here's what it looks like if you're on the ground. You have this big billowing cloud of dust just rolling along. And these are called harmatons. They have other names, but they're very severe dust storms. Anyway, so then and I took part in every element of this. We then assessed where we had good data and where we didn't. 1% of our data didn't process for some reason. We really didn't care. Next time we'll just throw those images out and substitute. But for this, we kept them. Then we looked at aerosol optical depth by comparisons to MODIS data for the same day, same location. And we had about a 95% success rate in that comparison. And for aerosol optical depth at 470 nanometers, we looked at the data above an aerosol optical depth of 0.6, and that totaled about 4% of our area, and that's in the B panel. Then 3 of us, myself and 2 of the geospatial people in the group, went through and we looked at every scene, each of us, and compared notes and resolved differences where we had residual cloud cover in the images. And that totaled just over 5% of the area. So 1% didn't process. So the total here is about 10%. We either had bad data or it didn't process for some reason or corruption of the data, or we had aerosol above 0.06 of the aerosol optical depth, or there was cloud cover. This is what it looks like under some of the dust storm conditions. You can't see the sun. This is a very, very high event, probably on the order of an aerosol optical depth of greater than 0.1 or 1.0. And that's really high. And that is Pierre Ernaud with 2 of his coworkers. And for some reason, he wasn't wearing shoes. And we all know about doing field work. Sometimes you dress in ways you wouldn't when you were in the office. Okay, so nevertheless, we mapped 700 million trees under all of these aerosol and cloud affected areas. Our interpretation, we were puzzled. Our interpretation was this shows the power of neural nets and convolution. Okay, who did the work? These are all the people who did the work, and we invited people to include their dogs. So we have several dogs with us, and it was a very diverse group of people. We're all still friends. I'm good friends with everyone on the team, and we didn't and there were no bad feelings where people wouldn't speak to each other. And sometimes with a huge research group, that's a major accomplishment. Okay, so now I'll just show a few examples of how we get ourselves out of the box of 10 billion trees and how in the hell do you use them in an intelligent way. So here's our viewer. This is online right now, and in our paper, in the methods section is a link to this. And the link is from the Polar Geospatial Center at the University of Minnesota. I'm leaving my presentation here with Dennis, and so people can access this and look at it. And then the important thing, if you use the viewer, is the URL will take you back to exactly where you were looking at on any computer, as long as it's not Internet Explorer, which doesn't work with Mapbox, because we had to use free things. We had a very finite budget. And so you can't use, you can use Firefox, you can use Google Chrome, Apple Safari 9 and above, Microsoft Edge 13 with the Win 10 update, and but you can't do this with Internet Explorer or other browsers. So now what we're going to do, and then I'll call it quits and take questions. We're going to look at this area in Niger in what is called the Aïr Mountains. And so now I'm going to zoom in progressively to this red box. So here we zoom in, and now we're looking at a polygonal representation of the tree density. So now let's zoom in further. So here we have a zoom factor of 11.3. Now we go to a zoom factor of 12. And now we see that in this particular area, there were 3 different images which were processed to make contiguous data across here. And they were from January, December, and December. So let's zoom into the red area here. Now you see and start to make the transition between raster representations of data and the polygonal representations of data. So let's go on farther. And now you can see what looks like the landscape has smallpox or something like that, but each one of these are trees. Now you switch to the satellite view, and this puts it into the context of where you are. You're in a drainage area, and then next we'll zoom in to the area here where we can see individual trees. So now we can zoom in to the highest level. You can click. So when I did this right here pertains to this image, and this pertains to this, and you can see the precise location in our data set, what the NDVI was, what the crown area was, and then our estimates via allometry of the carbon in leaves, wood, and roots. So I'll stop here and answer any questions. If anyone is really interested about the details, in our Nature paper, extended data figure 10 goes into all the machine learning things, what we did in a graphical form like this. And then, but these are things I've already showed. Very shortly, we will have an updated version of our viewer at the Oak Ridge National DAC with, well, no, it's already there, but we'll have the user's guide to it. And this PowerPoint presentation, which I put together, to guide people if you care to use it. So I'll go back. And I'll be happy to, thank you for your attention. I'll be happy to answer any questions.
We have plenty of time for questions, and Katie will be monitoring the Zoom questions, so she may intervene.
I didn't realize I was so quick because the clock hasn't moved.
Time flies.
There's one right behind you.
I beg your pardon?
There's one right behind you too, on the wall.
Oh. So what happened at 4:34? Or is that the real time now?
That's the real time.
That's real. Time stopped.
Yeah.
So I'm curious about, because you said you showed at one point a plot where you had multiple images from different years, right? So I'm curious how you use that. Do you use those, is that just because you don't get a full view of the entire Sahel in 1 year? Are you using them sort of to composite one picture together? And if so, think about interannual variability, and also about if you're if you're down near 1,000 millimeters, those trees are going to grow faster than the ones up by the Sahara. And if you're using data from, say, 2015 to 2021, right? It's not just one picture, I guess. So I'm curious about
so
it.
This is the first paper of this kind, and we had to use what data were available. It would have been great if we could have bought the data, but the data, if you get them from Maxar and were to buy them in bulk, they would probably cost you $5 or $4 per square kilometer. And we have 90 million square kilometers, and we don't have a budget of more than $100 million. So that's a problem.
If you did, you could build a football stadium.
Yes, yes. Or maybe give it to the scholarship fund as a positive complement to the football stadium. Now, when I was an undergraduate, it's just when they had Hughes Stadium down by the foothills, and one of the highlights was to go there when there was snow and have a snowball fight in the stands at halftime, and then we would leave. And then also in Moby Gym, when the team wasn't playing very well, people would fly paper airplanes down and across the court. And I think the engineering students made the best airplanes. Anyway, so yes, I agree with you. Good, it was a good comment, Dave. So to answer Ian's question, I'm not trying to slippery avoid it and slip away, but we had to use what data were available, and they covered many years, and so we just threw them all together. We realized there's uncertainty with respect to time, but we have all these data on the south side of the Sahara because there was interest of the people who bought the data from Maxar in that area. So it was Islamic instability. So this is one of the byproducts where sometimes you can find research which matches up with other things. So you can use those data for things totally different from what others may have done. So I agree with everything you said. Those are all liabilities and sources of variation and complications, but we did this with whatever data we had.
Can I ask a follow-up?
Sure.
So do you have somewhere you have maybe overlap for a particular area in subsequent years? And have you looked at interannual variability where you do have that?
Yes. Now in this presentation, we only used 1/3 commercial satellite images. We now have 800 million from the area, and we have a large number of data from late in the time period through the end of through March of 2023. And so now we think we can look at 2 time periods. That will minimize some of the questions you brought up. It won't alleviate them completely, but yes. And so we hope to look and see for most of the areas what the change in carbon has been. Dennis.
So Dave had a question about what was happening with the tree carbon after 800 millimeters. And I wonder if you've looked at the land use patterns and seen whether or not the fuel wood collection in those more humid areas would be starting to reduce the tree density and tree carbon in those areas.
Yes, it is. I suspect it's something like that. And so I'll talk to Matt Hansen at the University of Maryland, a good friend, and say, Matt, what do you show in this area with respect to intact woodlands of discrete trees? And see. But
I think even the human population densities are probably higher once you get in that area of 800 millimeters.
This is a good example of things appear in data like this, which you're very curious about, and you have to look at other sources of data or reanalyze what you did to see if you made a mistake. Question here?
Thank you for the presentation. I actually have 2 questions. One of them, so all of the data in this, all of the imagery in this whole band, geographic band, sub-Saharan or Saharan area, So the Maxar imagery was all available for all of this area to you because somebody else was capturing that before? Because you said that you have not paid
Yes,
for any
we were
imagery.
freeloaders on people from other agencies who purchased the data and prefer to remain anonymous.
Yeah, so there was imagery for all of this band of geographical area available for you.
Because of my interpretation, having worked in the area, is it was because of Islamic instability. So the level between classified imagery have spatial resolutions less than 30 centimeters. So the digital globe data, WorldView 3 is 30 centimeters, so it's just above that. And then WorldView 2 and QuickBird and GeoEye are 50 centimeter data. So that's why we could get those data and use them. So, but we were not working with any agencies across the river, as we say in Washington, D.C.
And so the second one, you had some discussion about identifying the cloudy scenes and dusty scenes and things like that. So have you removed all of them or?
No, in this study, no. But we have ways now of doing this. But ultimately, you have to employ people in the team to go through and double check all these. Now for cloudy imagery, two of my coworkers and I did review. So we divided things up, and then we ended up doing the whole area each and comparing notes. And there was a slight variation, but we trained ahead of time what to do and how to do it, and then got within at least plus or minus 1 or 2% the same answer. And what you saw was the average.
But the cloudy areas, your classifier was able to detect trees even in a cloudy scene?
Yes, we looked, and under high cirrus clouds, if they're not really deep, we were able to successfully map trees. Now, we don't know if we missed a lot of smaller trees and got the bigger trees, but my empirical look at things is that we were able to map most crown areas. In some areas, if the cirrus cloud was very heavy, that was not the case, and you could only map the larger trees. But we were astounded, and the editors at Nature were astounded when we reported that in the cloud and aerosol areas, we were able to map 0.7 billion trees. Now, we haven't compared the distribution. Next, we're going to compare the distribution of those trees to our distribution of all the other areas and see if the distributions differ. So there are many things like this you can do to get an idea what might have gone wrong, what went right, and what you should do in the future.
Thank you.
You're welcome. Yep.
Yeah, so this is more about the detection side of things. For any of the trees that you were out in the field and sampling things like height and things like that, were you able to look at if there was some threshold of either height or crown size that you were really confident above some, or if there was changes in the detectability?
Okay, what I'm going to do is I'm going to show you another presentation where there's a slide which deals with that.
Okay.
I don't think I have it in this presentation. Let me see if I do. No, I don't. Okay, I don't want to see that. Let's go to, I may need some help.
The envelope, the yellow envelope on the very bottom.
Folder.
Oh, this?
It looks like a folder, like
Go
a
to.
tab.
Over here? This?
Nope.
The yellow one, you got it? Yeah.
That?
Yep.
Okay, let's see. Huh. Well, I don't see it.
Oh, Kingston is to the left, that's your stick.
So that is this
No,
or here?
you can see it in the window you're looking at.
Oh, right there.
Here. Yep,
Thanks for your help.
of course.
So we're going to look. So also yesterday, I gave a seminar with two of my coworkers to the Google Machine Learning Symposia or something like that. And thank you. Thanks. So let's see. Date modified. Okay, so No, that's not right. Oh, here it is. Oh. So this is me in the grassland biome, but let me.
Don't trash it. Well, you could trash it, but you don't want to.
Okay, so here it is right there. Okay, so I'm now this has some of the same slides. So I'm just going to zoom down so I can answer the question that was asked. So I apologize for this. So now we're through my material. And so now we come to, oh gosh, maybe it isn't here. Okay, so I'm sorry, I didn't find the presentation I wanted.
That's
So
okay.
it's-
I'm
it's-
having lunch with you tomorrow too, so if you really talk about it then, that's fine.
Okay, let's see. Well, I'm having trouble finding this, so I hate to bore everyone with, so there's Kingston. So I know it's in the folder called CU. Oh, here it is. Okay, so believe it or not, I found it. Okay. Let's see, here's the smaller of the presentations. So now I'll go through and avoid what you've already seen, and I apologize for this. So now, so the question was asked about missing trees, right?
There's some size threshold, if you guys were able to do any, for the trees that you're collecting height information on the ground.
Okay, oh yes,
If you saw
okay,
any
thank
type
you.
of trends as
I
far
forgot
as
the
threshold you were
particulars.
confident of
So,
following.
okay, this is why you can't use field data to look at tree crowns. You can't measure the actual tree crown from the ground. So here, so we're coming to our data. So what we've done is we've taken tree crowns from ground measured trees. And we take the long axis and then the axis perpendicular to that, more or less in the middle. And then we compare that to a circular area of, with the long axis length. And you'll notice that you can make pretty big errors. And so we concluded from this, we can't use ground-based crown area data because unless you measure them very carefully, like cut down trees and measure them on the side in a systematic way, you can't tell what the crown areas are. You can't estimate them from the ground looking up.
What if you use TLS? We use terrestrial LiDAR to get an accurate measure of the tree count.
Well, that would be fantastic. So this can only be improved, but this is why we were very reluctant to use ground collected data from plots because of the inherent uncertainty in the actual shape of the crown. Whereas whatever it is, we measure it unless it was that weird triangular shaped tree, which was an error. Okay, there's one other question, Gabriel.
Oh, so one is on the shadows. So he said the tree has to be green, it makes sense. But on the shadow, we had a condition, so it has to align. So can you say a little more about how you use the shadow constraint?
Sure, I think I may actually have it in here. Let's see if we do. Okay, so here's the same image which I showed before. And so what I noticed when I was working on this image was up in here, so let's take this tree. You have shadows all around this very weird tree. And anytime you see a tree like this, you think this is not a tree, it could be 3 trees, but this turns out to be a bush conglomeration that was green. And these are the shadows, because when bushes grow, you'll have a bush like this, and then there'll be a shadow next to it. And so anytime you see something like this, and then zoom in from imagery, say from Google Earth, excuse me, you'll see that you're in a bushy area, and as opposed to say areas down here where you have a distinct tree. So it was simply going into the panchromatic data and the MDVI data for this particular area, and then insisting that the shadow be away from the tree crown and in the direction of the incoming solar flux. So we've now added that to our machine learning. Now, we also mapped trees in the Atlantic Ocean, and we thought, oh, what the heck have we done? So I investigated, and it was an area off the coast where there were a lot of whitecaps. And So behind the white cap, it was very dark because there was a shadow cast from the back of the wave crest. And in the frothy part of the crest, there was a slightly higher NDVI value than there was red. And so the neural net detected that as being a tree. So our solution there was to have a water mask and just say, this is impossible. So with a neural net, you'll find some pretty weird things that happen sometimes, but it's a very powerful tool. Convolution is a very powerful tool.
Oh, great. So the follow-up would be, so what are the other variables, what features for the machine learning? So you got a tree crown.
Okay, it was the most important ones were a green tree crown like this, and it had to have an associated shadow in the direction away from the tree, in the direction of the incoming solar flux. So for example, here's a good example. Here's a tree, we don't know how tall it is. Here's the shadow which is cast. Now here are two more trees. So we expect something, it doesn't have to be this pronounced because this could be a very, very tall tree. But you see in all of these areas, you don't see anything like that, and you see shadows all around like this. And so I concluded those were bushes and then confirmed that by using Google Earth. But it's time consuming. So 7 of us did this for like a month and a half. And then our statistician, Jorge Pinzon, had to organize things. And then we double checked everything again. So it was fun. We learned a lot, but you wouldn't want to do it all the time.
So he's looking for graduate students.
It would have to be a graduate student because undergraduates, who knows what would result.
Well, let's thank Compton. We have a reception set up, I think, starting at 5 in a few minutes, or they may be set up now.
We're good to go.
Okay, so wine, cheese, snacks out in the atrium. And, okay.
I was a few minutes late, some meetings.